going to explore actually using these properties of logarithms and exponential functions to use them for what we intend to use them for, which is finding unknowns when we have logarithmic or exponential models for something. Okay, so we say, taking into account example number 6 I've got listed here, it says we've deposited $1,000 in an account that pays 6.25% interest, and that's compounded continuously. Okay, and what that tells us is we're going to be using a continuously compounding growth model, which says the amount that we have is equal to the principal, or the beginning amount, times the base e to the power of the rate times the time. Okay, so it says how long is it going to take our money to double. So you'll notice in this instance, we're already aware of certain things. So we are aware of our principal amount p, and we know of the rate r here. So we know p, we know r, and the thing that we're being asked to find is actually the time, which is up here in the exponent. So we're going to have to plug in what we know to go find what we don't know. You might ask yourself, well, do we know this capital A over here? But if you notice in the last question here, it says, how long is it going to take my money to double? So for instance, if I started with $1,000, then what I'm saying here is my money to double. This kind of represents the amount at a given time. And we say that that amount would be like $2,000, okay? So our job is to find this time. So what we'll do is we'll set this up. We say capital A, we want to be $2,000. We say the principal amount, principal investment is $1,000. The rate is 6.25%, which we are going to write as 0.0625. We have to write it as a decimal. And then we don't know the time. We say don't know. So setting this model up, we get $2,000 is equal to $1,000 times the base e to the power of 0.0625 times our time, and we're just going to leave that time out. We don't know the time. But see, here's the thing, we actually want to solve for this in this case. So this is pretty cool. We actually know how to do this now. What we're going to do is we're going to isolate the base of this expression. So in this case, we say e to the power of something, that's our base. So we're going to have to divide both sides by 1,000. Divide this by 1,000, divide this by 1,000. Looks like what we get here is on the left side 2. And on the right side we have e to the 0.0625 times the time. So now we need to get rid of this e to the power of. Now this is an exponential expression, so what we're going to do is we're going to use a log to undo this exponential expression. We're going to use a log with the same base. So we say ln of this is equal to the ln of this. We're really using the one-to-one property. So we say log base e of something that is base e to the power of something. So logs and exponential things with the same basis cancel out. We get left with this. We say the ln of 2 is equal to 0.0625. That's a 5 times t. So now we'll just divide by this decimal here, which is a very small decimal, 0.0625. And we get this right here. We say then the time must have been equal to this expression right here where, we say ln of 2 divided by 0.0625. Let's clear this out. We say ln 2 divided by 0.0625. We get about 11.09. Okay, so we're going to write this in, and we say 11.09-ish. And we want to label this, and what we were finding was a time. So basically, we were finding the time condition that allowed our money to double under these conditions where we started with $1,000 and we're getting this amount of interest. It says how long does it take it to double? We can actually solve for that now. Okay, so now that was an example of solving an exponential equation. Let's look at an example of solving something logarithmic. It says the number y of endangered animal species on a protected wildlife preserve from 1990 to 2004 can be modeled by this. So we have this model right here that kind of just says this is approximately what was happening to the population y as the years t went by. So we say t represents the year. With t, this should be equal to 10. Corresponding to 1990, okay? So we say between 10 and 24, determine which year the number of endangered animal species reached 342. Okay, so what we have here is a situation where we've been given this, which is really a y value, and we've been asked to go find the time. Again, go find the time. So we get this here, we say 342. Let's plug this in, and we're going to work backwards, and we have the tools necessary to solve this equation now. We say times the ln of the time. So we are going to isolate this base this time, except for the base is this logarithmic expression. So we say, let's go ahead and add 117 to both sides. So plus 117 here. These cancel out. We get left with on the right side, we have 159 of these natural logs of t. And on the left side here, it looks like it ends in a 459. So now we're going to divide by 159 on both sides, which, you know, you look at this and you say, I'm getting this very ugly expression. And you know what? It's not the prettiest expression, but it is exact, okay? And that's what we want. So we have this fraction right here is equal to the ln of t. What we're going to do now is we're going to take this logarithm, we'll just rewrite it into exponential notation, which our base here is e, mind you. So we're saying e to the power of 459 159ths, okay? This is equal to t, which is, this is what we want. So we're going to go type this in. We say e to the 459 159. So we say e to the 459 divided by 159. This is what I want. And we would say, well then, 17.936. So I'm going to write this down and we say t equals 17.936. Now, the thing we need to do is recognize that this is a year. So it's like year 17.936. But keep in mind, t equals 10 corresponded to 1990. So I was asking, what year does this happen in? Well, you know, 17.936 is 7, you know, it is 7.36936 years after 1990. Okay, so we would say that this is actually 1997.36, which, you know, it's wherever we are around the sun. But that's the year that this thing happened in. Pretty cool. We can use our properties to solve for this.